In this lecture, we're going to continue to talk about the application of gradient descent, but this time for classification objective. And this is going to be done by means of logistic regression model, which is essentially used to model the probability of a certain class or event existing, such as in some binary form, such as like pass or fail, win or lose, healthy or sick, and so forth. And this can be extended to model several classes of events, such as determining whether an image contains a cat, dog, lion, and etc. So this can be extended once again for multi-class classification purpose. And later, we're going to also talk about the regularization technique so as to prevent overfitting and enhance generalization. So as such, this is what we're going to talk about. So we're going to talk about motivation so that we can essentially try to identify the logistic regression model for the purpose of classification. And then later, we're going to talk about regularization, the concept of regularization, in order to solve the overfitting problem so as to enhance, once again, generalization. So before, what we had done was essentially using linear regression for the purpose of connecting the dots. But here, what we're going to do is to delve into classification task, where, for example, a classification task is to classify, like in this binary situation in email, whether it's spam versus no spam, or for the ATM machinery, currency check could be, is there some fraudulent, yes or no? Or once again, for a patient being or having malignant versus benign cancer and so forth. So essentially, to simplify the problem, let's just delve ourselves to only a binary situation. So what it means is that the label is going to be either 0 or 1, or for 0 being the negative class, or 1 being the positive class. So previously, as I said, we sort of began talking about using or the application of gradient descent model for the purpose of linear regression. So given at that time a set of these samples, what we did was to essentially to come up with the best line fitting model. So if we have the such line fitting model, that is to have the linear regression model, then in this case, the best connecting model with just these samples. Let's just take this one here out for now. So let's just say that for now we only have these samples. So based on these samples, the best line fitting model would be, let's say, this. So in this case, we can still use the linear regression model for performing classification. That is, for example, as you can see, for the threshold classification output, in this case being, once again, the hypothesis model with just a simple dot product between the parameter and the feature, is that if the dot product itself is, say, greater than 0.5, which happens to be, say, here, and above, then we can say that the output label should be to say yes, that is that the tumor is malignant. Or if it is less than 0.5, we can say that the label is, say, 0. So what that means is that, as you can see, with these nicely situated samples, then 0.5 would be somewhere here. So using 0.5 would actually indicate a decision boundary to be somewhere here. So if the tumor size is, say, somewhere around here, and then if it is multiplied by or using the dot product of the parameter, then anything that's going to be, say, less than 0.5, which would be these, let's say, samples, then they would belong to, for example, benign. And these samples, which turns out to be, as you can see, because they are above or greater than 0.5, then the label should be predicted as being, say, yes, or having tumor or malignant. On the other hand, let's just say that we have one more sample. That is, we extend the sample, and then that sample happens to be situated right here. So with this new sample, then the linear regression model, which is, once again is going to be having this form, because linear regression, the objective of linear regression is to come up with the best fitting, say, hyper plane, or in this case, it's going to be just a straight line. Because of this added sample, that hyperplane or linear line is right here. Now, what that means is that by using, once again, the same analysis, that is using, say, performing exactly this, that is, say, the dot product between the parameter to that of the feature is going to actually move the threshold somewhere here, because as you can see, 0.5 is here. So anything greater than 0.5 would be right here. So this now, before we had the decision boundary right here, now the decision boundary happens to be right here, which then is going to be problematic because, as you can see, these are the samples, obviously, that belong to the malignant case. So this one here is obvious. I mean, it's very much malignant. But what about these samples here? Now, because of the fact that the decision boundary has moved from left to the right by this much, that automatically makes these samples to be, for example, not belonging to the malignant case. So that's going to be problematic if we indeed just use the linear regression model, which is this, as is for the purpose of classification. Now, for the classification, once again, in the binary class, that is the label of y being either 0 or 1, the hypothesis function therefore can be either much greater than 1 or much less than 0. So that's another limitation for just using the hypothesis function using this linear regression. So that's why we want to introduce the concept of the logistic regression, where the logistic regression essentially is a probabilistic model, wherein in this probabilistic model, it represents by using the probability, that indicates which class that it belongs in terms of the level of probability. And it is also bounded between 0 to 1. In other words, the logistic regression function, by using the logistic function or sigmoidal function, is going to be bounded between 0 to 1, which would be much better than having the hypothesis function to be, let's say, greater than 1 or less than 0. So this would be much fitting to the classification type of application. So, for example, the logistic regression model is a hypothesis representation by using a sigmoidal function that looks like this. For example, once again, if you want the hypothesis function to be bounded between 0 to 1, wherein that within the hypothesis function itself, before, for the linear regression function, it was just a dot product between the parameter to that of the feature. But now with the logistic regression function, which is actually a mapping of this dot product between the parameter and feature with this nonlinear function g. And this g function is the something called the sigmoid function, which looks like this. It is also called logistic function. So these are synonymous to each other. Meaning that, as you can see, the g function itself or the new hypothesis function, which is called logistic regression model, now has this type of function, so that at the let's say z, which is z, would be theta transpose to that of x, which is essentially a dot product between once again the parameter and the feature. Depending on the value of it, is that if it is 0, then it's sort of like is the boundary, and so g of z in that case is going to be at this point is going to be at 0.5, and anything greater than, say, this way, the positive of z would indicate the positive side of g of z, and the negative side of z would indicate the negative side, that is a value between 0 to 0.5. And once again, for the positive side would be between 0.5 to 1. So here, in order to indicate this logistic regression function, is that we have this parameter theta, once again, and then this is dot producted with the feature, and this feature, or this z, then is then mapped into this sigmoidal function. Now, we can also interpret such hypothesis function using logistic regression model, is that it can be used as an estimation of the probability of the output label being equal to 1 on the input of x. For example, suppose if the feature happens to be, let's say, just binary in this case, x0 and x1. Well, x1, by the way, is just a bias. So x1 would be indicating the amount of the tumor size. And let's just say that using this, once again, this hypothesis function using the logistic regression, let's say that value indicates to be 0.7. So what this 0.7 can be interpreted as is that this particular feature will indicate the output to be 0.7, which means that the patient with having this tumor size would have 70% chance of having tumor being malignant. So this particular logistic function is to be used by using, again, this logistic function is to represent essentially the probability that label being 1, that is that the tumor being malignant, is given the amount of feature, which is this, which is parameterized by theta. Or the same thing can be said in this way, is equal to the probability of the label being 1, once again, label being 1 being that the tumor is malignant, given the particular tumor size, which is parameterized by theta. So the label here could be either 0 or 1. So therefore, the sum of the probability of both cases, the 0 as well as that of 1, should be equal to 1. Or you can also obtain one of the two, that is the output label being 0 would be 1 minus the label being equal, the probability of the label being equal to 1. In other words, essentially what I'm saying here with this slide is that we can then use this model here, which is the logistic model, can be used to estimate the probability that y is equal to 1 on the input being a particular x. So, for example, once again, this hypothesis function using the logistic function is essentially the probability of the label being equal to 1, given that the feature is equal to x, which is parameterized by, say, theta. So in short, this particular logistic model is this, which looks like this. So in this case, we can predict, for example, once again, the y being equal to 1 if, for example, the hypothesis function itself is greater than equal to 0.5. That is, if it is 0.5 here, we are talking about here, right here, right? So this means that anything that that belongs here for the z, where z once again is the parameter dotted with that of the feature. So if z happens to be ranging from here to here, then it should be positive, or it should predict at the label predict to be positive. And on the negative side, if y is equal to 0 instead, we can predict y to be equal to 0 if, for example, the hypothesis function then is less than 0.5, which means that we're talking about this region here, right? So if it is less than 0.5, we're talking about right here. So that means that the once again z, which is a parameter transposed to that of x, being somewhere here, will say that the label should be predicted to be equal to 0. So what does that mean? So here, by using such a representation, then we can then obtain a specific, say, decision region or decision boundary. Let's just say that, for example, we have a situation with, say, positive labels samples versus those of the negative label samples. So these are the positive samples, and these represents the negative samples. So obviously, in this case, we can say that the samples are nicely situated in a linearly separable situation. Now, in this case, we're going to, rather than obtain a theta by using some iterative process, and that iterative process, by the way, is by using the gradient descent. So we're not there yet, but we are heading toward that direction. But suppose that by some wisdom or by some experience, let's just say that we were able to know the theta, the parameter being a three-dimensional parameter, with the first one being -3, the second one being 1, and the third being 1. So in that case, that hypothesis function, right? Hypothesis function is g over this, say, the dot product of a parameter to that of the feature. So therefore, as you can see, the x bar, for example, would be x0, x1, and x2. And typically, we have said that before that x0 should be equal to just a bias being equal to 1. So in that case, as you can see, using this dot product situation, then inside here, which is theta transposed to that of x, then would be equal to, say, theta 0 plus theta 1 x1 plus theta 2, say, x2. Now here in this case, once again, by once again having these thetas being assigned here rather than iteratively solved, assuming that by just taking these parameters as is, then as you can see that inside of this parenthesis is going to be just 1 plus, as you can see, 1 plus theta 0 is equal to -3 plus x1 plus x2 is equal to 0 is what this is, right? Theta transpose x bar, right? So what this means is that, and then as you can see, the boundary, remember the boundary says that g of this in this logistic regression function with z being say theta transpose to x is that if it is equal to 0, that's sort of like sets the decision boundary. So we need to set that equal to 0 for this logistic regression function. So this means that the inside of the parenthesis is equal to this, and we need to set that equal to 0 in order to obtain the decision boundary being h of x being, or the hypothesis function being equal to 0.5. Now, so what that means is that if you set that equal to 0, this is what we have, and essentially this is what we have then. So this essentially establishes this decision boundary, and as you can see, that x1 plus x2 is equal to 3 is specifically this particular line, right? Actually, it's a little bit offset. This should be actually 3, and the cross section should be also 3 here. So the cross section here, the intersection is what I meant to say. Intersection should be 3 on the vertical axis, and similarly on the horizontal axis, the intersection should be equal to 3. So that means that now with the decision boundary being, that is decision boundary using the hypothesis function being equal to 0.5, what it says is that inside of the parenthesis, which is this, is that we should predict y equal to 1, the positive side, which is this, if, as you can see, right, the parameter transpose to that of x, which is the parameter dotted with the feature, is greater than or equal to 0. So hence, you come up with this decision boundary representation, as well as y, the label being equal to 0. So this one here represents all those samples that belong here, and for those samples that belong to say less than 3 would be these samples. So as you can see, the logistic function would actually allow us to be able to come up with a decision boundary in this linearly separable problem. What about linearly non-separable problem? So we can also apply the similar situation, and obviously in this case, this would be a linearly non-separable situation or scenario. So those of the red samples would be those of the labels having positive, and those of the samples that belong or that's closer to say 0 would all indicate being negative samples. And so in this case, the way we can do is that once again with some wisdom or some some help from the knowledge base, let's just say that we were able to have theta, the parameter, to be identified as this. So in this case, actually, it would nicely give us this decision boundary. That is, that by using, once again, the same hypothesis function, which is the logistic regression function, g, over all of the, these parameter dotted with that of x. Well, actually, I should actually just maybe say theta bar dotted with, say, x bar. Now, in this case, by the way, we have a different type of x situation here. It's not just x1, 2, or 3, but, and as you can see, these parameters would be theta 0, theta 1, theta 2, theta 3, and theta 4. So we have 5 entries here, or elements in the, theta, or the parameter vector, whereas for the x vector would actually be x0, x1, x2, x3, x4, right? Where each of these x would be, well, the first x0 will be equal to 1. In this case, x1 would be equal to x1, x2 would be x2, but x3 would be x1 squared, and x4 would be say x2 squared. Okay, so we are going to have this mapping as far as feature is concerned. So with that, having these two dotted with, then we then obtain, say, this situation. And so with this mapping, that is to obtain this linear regression mapping, which is a dot product between the parameter to that of the feature, is that we can predict y being equal to 1 if once again, the inside of this parenthesis being by applying these values, right? That is that theta 0 is equal to -1, because x0 is equal to 1. And then x1 is equal to 0. So this one actually goes away because x1 is equal to 0. And theta 1 is equal to 0. And similarly, theta 2 also is equal to 0. So this one also goes away. And theta 3 is equal to 1. And theta 4 is equal to 1. So what that means is that inside of the bracket or parenthesis can be then said like this, right? Once again, at the boundary, that is so if we just have collect all these terms, the first one being -1, the second one being, say, x1 squared, and the third being x2 squared. So if it is greater than or equal to 0, right? If it is greater than or equal to 0, once again, so that means that we're going to be here, right? So right here is where we are. If it is greater than or equal to 0, then we are talking about this region. So it should be labeled as positive. And similarly, you can do the same for the negative region, right? So what this means is that we can take, say, -1 on the other side of the equal sign, which is this, right? So in other words, because this is binary, you don't actually, I mean, it's going to be, y is going to be 0 if, for example, the whole thing is, say, plus x2 squared is less than, say, 1, right? Which would be the opposite case, which would be then this region here, which would be belong to this region. So nicely, what that means is that this obviously is an equation, a formula for a circle. So that circle is defined by this. So those features that with a combination of x1 and x2 being, say, greater than or equal to 1, so which means that those of the samples that is outside of the circle, which would be these, would have the label of being 1. And similarly, for those of the samples which is inside of the circle, indicated by this, is going to be given with a label of 0. And we can also design, therefore, a very, very complex decision boundary that looks something like this, rather than just a plain circle like that, which is indicated by here, by designing, once again, theta transpose x bar, right? So if we can come up with this representation, we can then, and once again by using the logistic function, then we can then design a decision boundary that looks pretty much complex like this. So that means that, once again, as you can see, this is still linear regression function. So this is still linear regression function, as you can see, because we're talking about, once again, exactly the same thing as this, where, once again, these are the theta 0, theta 1, and so forth to, say, theta whatever, say, m. So this would be m plus 1, say, dimension, and it is dotted with, once again, the x bar, where x bar could be starting from x0, x1, say, to xm, where, as you can see, some of these features could be, say, multiples of other features as well. For example, what I'm saying is that this one is, for example, obviously it would be same as say x3, and this one would be say x4. This one here, combination, which is the product of x1 square and x2 square, would be say x4 and so forth. So by having or designing this dot product, you can then build a very complex decision boundary. Okay, so we sort of like talked about how we can design a decision boundary that is anything that's complex using some predefined information or prior knowledge, but we could also obtain and train for the parameters using the training data set. In other words, suppose you have a training data set like this. So we have n number of the samples, of the training samples, right? Which can be then described by this m, well, which can be m samples, but for each of the sample, by the way, each of the sample is m dimensional, or I should say m plus 1 dimensional, where x0 is normally typically is equal to 1 as given as the bias. And the output in this case, let's just say that we just have, once again, binary classification case. So y label is either 0 or 1 or positive or negative. And we have this hypothesis function, which is logistic function. And the question here is, before we were able to just plug in theta, the parameter, because of, once again, that they were defined from some prior knowledge base. But then our real question is, how do we then choose the parameter theta rather than but using the prior knowledge? How do we then obtain the parameter theta? So we then train for the parameters using the training by data by means of the gradient descent algorithm, which we have done for performing linear regression. So in this case, what we need is would be some sort of a cost function. And remember, in the linear regression model, we used a j of theta, where the j of theta essentially was this, right? If you can recall, it was actually 1 over 2n sum of from I1 to n, where n represents the number of samples, and you have the square of the differences between the prediction by the hypothesis to that of the labels, right? So the prediction versus that of the label values are subtracted each other to compute the error or the difference between the two, and then we square. And then what we did was that we summed for all of the samples. There are n number of samples, and we divided by 2n. We essentially obtained an average value of the error, or we call this as the least squares. Whereas the 2 here came, right, if you can recall, was just there for the purpose of mathematical convenience. Now, we're going to be using exactly the same representation, but for the logistic regression, what we want to do is to modify this representation slightly differently, so that, first of all, what we want to do is to take this 1/2 to inside of the summation. So this is actually put in there. So now, based on the linear regression model, we're going to turn into the logistic regression model by, once again, taking 1/2 inside of the summation. And it's actually not changing very much. It still looks exactly same as this. And what we want to do is to say that this much here is the cost function. So the cost of making a decision or prediction by using this logistic regression model to that of the label, right, would be essentially one half of the square of the difference. So this would be the cost for making a prediction for each of the sample, okay, for each sample. Now, the prediction model, by the way, we're going to be using logistic regression model. So we're going to call this logistic regression. Okay, so this is the logistic model, where the logistic model is essentially this. Is this using the sigma order function? Now, when you do this, for example, when you square this logistic model as is, and then you square and then and summing all the samples, then the J function, which turns out to be like this, is going to turn into a so-called non-convex function. Non-convex function is one that has these local minima. And we said that convex versus non-convex is that for non-convex, when you for example, any two say points on the non-convex function, when you say when these two or any random samples are connected, then the line, we can actually tell the difference whether it's non-convex versus convex, is that for non-convex, if any two connecting say points, any line that connects these two points, if it goes through two different regions, two different, say those are the regions that's in the, say, the red versus those of the green, and obviously here this line goes through the two regions, right? Number one and the number two. So this obviously tells you that it's non-convex. Whereas for a convex type of a function would look something like this. So that is any particular two lines, right? Or I say 2 points once again, with a line that connects these two points. If it does not go through the two regions as like that of the non-convex, then we say that it's a convex function. Okay, so here what this convex function also tells us is that here the global minimum is obviously guaranteed, and there's no local minimum. Now, the problem with using the once again this logistic function, or the sigmoidal function, for performing this cost function is that this is going to give you a non-convex error function. That is to have these local minima, which means that the global minimum is not guaranteed. So the question is, how do we then avoid having the the local minima and still perform the gradient descent, so that we can actually obtain this global minimum, where that global minimum, remember, by using the gradient descent, essentially tells you this, let's say if it is two dimensions, say theta 1 and theta 2, for example. Okay. So to make it into a convex function, the logistic regression cost function is going to be transformed by using negative of the log function for both, say, labor 1 as well as that of labor 0. For the labor 1 case, we map it into negative of the log of the hypothesis function, and for the labor of 0, we map it into the negative of the log of 1 minus the hypothesis function. So let's look at both cases. First, let's look at the label 1 case. So the positive case. Here, once again, the objective is to make this cost function or the error function to be convex. That is, to make it very smooth function so that there's no local minima and global minimum is essentially guaranteed. So in the case of, once again, for the label of 1, this would be the cost. For example, once again, mapping this prediction hypothesis with a negative of the log. Now, this is the cost function, which is the negative of the log of the hypothesis function. By, for example, looking at the log of z itself, which looks like this, where, as you know, for log at being 1, it should cross at 0. And if log of the argument is anything less than 1, it's going to essentially approach negative infinitive. So to make this to the other side, the positive side, looking like this, we want to place a negative sign in front. So this is where this particular function comes from. At the same time, while this is positive now, we also can get rid of it, of this part of the tail end by noting that the hypothesis function itself is actually limited between 0 to 1. If you can remember that this hypothesis function is essentially 1 over 1 plus e to the minus, remember a dot product between the parameter to that of the feature. So this function, which is sigmoidal function, is essentially limited between 0 to 1. So this means that the negative of the log function for the cost just happens to be stretching from here to here, where the when, for example, the hypothesis, the prediction is near 0, it goes to infinitive, and if the hypothesis is, say, near 1, the cost is going to be minimized to 0. So that's going to be true for label 1, and as far as cost is concerned, it's essentially what it is, right? For example, if label says yes, which is positive, and as well as the prediction says also positive, then the cost should be 0. And this is what you have here. On the other hand, while the label is 1 and the prediction says 0, then the cost should be very, very high. So that's exactly what we have. As long as we have, for example, prediction to be the opposite side, say 0, as opposed to the label being 1, label of that particular sample being 1, when the prediction is 0, then the cost is very, very large. So it captures essentially the intuition that if the prediction is 0, meaning that the prediction or the probability that given the feature parameterized by this parameter, and the prediction that the label being 1 is essentially 0, but let's say the sample's label itself is already 1, which is actually the opposite case, then we should penalize the learning algorithm by a very, very large cost. So this particular, the negative of the log function, which is this, for the label being 1, looks very, very appropriate. And similarly, for the case of the label being 0, we place a negative of the log of 1 minus the prediction. And similarly, the negative of the log of 1 minus z is essentially has this type of function. So we apply that directly here. So in terms of the cost, this is the function, the cost function. So once again, for the case of label being equal to 0, such that, as you can see, that if the prediction says 1, which is right here, when the label of the sample is equal to 0, then the cost should be going really high. On the other hand, if the prediction says 0, as well as the label being 0, then the cost should be equal to 0. So for the negative side, the y, for example, the label being equal to 0, this function seems to be very, very appropriate. So together, that's what the cost of each of the sample, the ith sample, is made up. That is of two possible cases, the label being equal to 1, as well as the label being equal to 0. Okay, so you now saw that this particular cost representation is for a single training sample, where for a single training sample is divided into two cases, one for the label of the sample being 1, which is this, and for the label being equal to 0, which is given by this as far as the cost function is concerned. And for a single training sample is this, but we have n number of samples. So what you do is that the entire error function or the entire cost is essentially sum of all these individual costs for each of the ith sample. And then what you do is that you sum all these individual costs, and then you divide by the number of the sample, which is n. So this means that j of theta, which is the error function, essentially is the average cost of making mistakes. Now, there's another thing that we also need to observe is that now this cost function for a single training sample is divided into essentially two parts, right? One label being y equal to 1 with this, and y equal to 0 being this. So here, what I want to do is that maybe we should combine these two together into one mathematical statement. So this is the way we're going to do that. That is by multiplying the first term by y. So we have this, y is multiplied by negative of the log, which is this. And then we also have this one here, the second term multiplied by 1 minus y. So by doing so, we can then combine these two into one mathematical statement. And this is because, as you can see, y is either 0 or 1 always. So for the case of y, for example, being 1, this means that the second part actually goes away. So we only have this part, which essentially captures for the case of the label being equal to 1. And similarly, when the label happens to be the other way around, that is, let's say being 0, then, as you know, this term being 0, the whole thing goes away. So we now just have this with y being 0. So that's going to be just this, right? So the entire mathematical statement essentially collapses to this for the case of y being equal to 0. So this is a good way of combining these two statements, 1 and 2, into one. So once again, what it means is this, right? For the label being 1, the cost is going to be collapsed to this. And for the label being equal to 0, the cost is going to be just left with the second term. Okay, so now, okay, so we sort of like saw that the cost function is going to be a convex function with respect to the error. That is, if you have the error function looking like that, the error surface is going to be essentially a very, very smooth function, meaning that there's no local minima, right? So then you can essentially obtain this particular location where, for example, this theta star would indicate that of the global minimum for this error function. So now we were able to do this, that is to make very, very rough surface into smooth surface looking like that by mapping the cost function by using negative of the log function. Okay, so this is what happens, right? The entire error function now becomes the negative of 1 over n of the sum of these two terms. Okay, the negative comes because of the negative of the log functions that which we just talked about. So this is the final result as far as the error function is concerned. And what it means is that as far as theta is concerned, this the error function with respect to theta, this function looks like this, meaning that it's a very, very smooth function. Now, the next thing that we want to do is to be able to search and find this global minimum. And how do we do that? That is to be able to obtain this theta star. We need to be able to obtain theta by minimizing this error function with respect to theta. Now here, once again, we have one thing that we have to also keep in mind is that the output, which is the prediction, which is in the form of hypothesis function, looks like this, which is a sigmoidal function. So this one here, what it means is that essentially that it represents the probability that given the feature, the label of that sample is positive, or the label is equal to 1. So this one here, this function, essentially represents the probability of the sample belonging to the class of 1. And so the question is, how do we then obtain this theta that will perform this realization of this particular prediction? And we're going to be able to do this once again by means of this gradient descent process, where as you can see, it's an iterative process as we have seen it by means of the linear regression case in the last lecture. So given once again this convex function of this error function, what we want to do is to minimize this error function with respect to theta. So the question is, what is theta? And we can do this by, once again, using this iterative process called gradient descent. Okay, and how does it work? Well, so this is the way it's going to be done. That is, the current value of the theta is going to be equal to the previous value of the parameter theta plus the change of the parameter. So for example, theta j is equal to the previous value plus the change of the parameter theta sub j. And this change of the parameter theta j is essentially the negative, right? The negative of the alpha times the gradient of the cost function, dj d theta j, right? So this one here. So this is where this term comes from. Is essentially the change of the parameter value. And this is going to be done iteratively. That is, we repeat this process again and again. And so what you do is essentially you take the partial derivative of this cost function with respect to each of these parameter theta sub j. Now, so what is the result going to be? The result is going to be, as you can see, the partial derivative of this is going to become essentially this. That is, by taking the entire cost function, and then you perform partial derivative of that with respect to theta sub j, is going to essentially arrive to this this quantity. That is, it's 1 over n of the summation of the difference between the prediction to that of the label, and then it is multiplied by the feature. Okay, which feature? The ith feature. And you do this for all of the for each of these parameters. I'm sorry, I should say you make the summation for all of the samples that you have. Okay, so how many samples we have? N number of samples. The J here indicates, by the way, is the dimension for each of the sample X or the parameter theta. Okay, so for example, the parameter theta would have essentially m plus 1 dimension. Okay. All right. So the question is, how do we show this? How do we show that the partial derivative of this error function is going to become this? Well, first of all, I should say that this particular representation, by taking this partial derivative of the error function, is exactly same as that of the linear regression case. Okay, it's exactly same as that of the linear regression case. Right now we are doing the logistic regression. Wherein we had to transform the hypothesis function into by going through taking the negative of the log, so that the error function becomes essentially a smooth function or convex function. On the other hand, at the same time, it just turns out that by taking the partial derivative of the error function, it's going to still give you exactly the same iterative